Again, welcome to Biostatistics. In this lectures, we're going to study the basics of hypothesis testing. And again, this is our first lectures on hypothesis testing. So our main objective is to go through what is a null and also alternative hypothesis, what is a test statistic, what is p-value, what is significance level, also one sample z-test, and then power and sample size. So review of, again, the basic of inference. We say population again is all possible values, everything. Then a sample will be the portion of the population. And also we said inferential statistics is generalizing from a sample to a population with a calculated degree of certainty. So inferential statistics is deal of having a sample, working on a sample, test the sample, the result that you get on a sample, you are going to apply it to the whole population. And we have two forms of inferential statistics. One is hypothesis testing and also estimation. So we're going to start with the hypothesis testing. So first, what is a parameter? We say the parameters are the characteristics of a population or a numerical characteristics of a population. Example would be the population mean or population proportion or a population standard deviation. So it's a numerical characteristics of a population. Then a statistics is a calculated value from data in a sample. So that would be the characteristics of a sample, a numerical characteristics of a sample. And from our previous lectures, we explained the difference between the parameters and also statistics. Again, parameter source is from population, and the notation can be mu for mean. In statistics, normally it comes from sample, and we have an X bar for the mean. And also the parameter doesn't vary, and also we don't calculate it. But with statistics, we always calculate it. Calculate it, yes, and also we may take two or more statistic samples. We may take two or more samples, and again, the mean values or the standard deviation may be different, so it varies. Then we say the inferential statistics concept is taking a sample from a population, then testing the sample. The result you get, we apply it to the population. So we start with the introduction to hypothesis testing. In some textbooks, we also refer hypothesis testing to be a significance testing. And the main objective of hypothesis testing is to test the claims about parameters. So it's to test the claims about population characteristics, parameters. Example can be the mean, proportion. It can be also be, if we are doing regression, again, it can be the slope also. So again, hypothesis testing, main objective is to test the claims about a parameters. The first step in hypothesis testing is to state our problem. Then we have 4 more steps. So the first step, state the problem. Second step, we are going to state the null and also the alternative hypothesis. The null is always refer to the population, no difference. Then the third step, we have to do our test statistics. In these lectures, we're going to use our z-score to do our test statistics. Then the fourth step is to use the standard normal table to find the p-value, the probability, whether we should accept or reject HO or HA. HO is the null hypothesis, and then HA is the alternative hypothesis. So again, this is the first step. After we state our problem, we're going to get our null and also alternative hypothesis. Then we test our statistic. Then we find the p-value and we do our interpretation. Then also the significance level. And most important is to understand all the 4 steps of testing, not just the calculations, because at the end, we have to again interpret our results, whether we accept HO or reject HO, which is the null hypothesis. So we start with the null and also the alternative hypothesis. Here we say we're going to convert the research question to null and also alternative hypothesis. So the null hypothesis again is HO, and that is the claim of no difference in the population. So example, we may do a test saying that, okay, we know in 1970, the average weight of male between the age of 20 to 30 is 200 kilograms. That is 1970. Today, we don't know. So we want to test whether it's more than, greater than 1970 or less than 1970 claim, which is 200 kilograms. So our null hypothesis will be the 1970 value because we know. And so that is 200 kilograms. Now we want to check in 2020 if the weight is greater or lesser than the null hypothesis. So here the alternative hypothesis HA will be the claim of difference. Always the alternative hypothesis will go against the null hypothesis. So always we want to seek an evidence against HO as a way of what? Bolstering the HA. Always the HA is against HO. So let's see an example here. Hopefully this will make us understand it more. So example here is about body weight. And our statement of the problem is that in 1970s, between 20 to 29-year-old men in US had a mean body weight of 170 pounds. We can see population mean, so we know the whole population in 1970s between 20 to 29-year-old men, their body weight is 170 pounds. And also their standard deviation is 40 pounds. Now we want to test whether the mean body weight in the population now differs in 2020. So in this case, our null hypothesis, which is HO, the mean will be 170. And then the HA can be either greater than 170, less than 170, or not equal to 170. So here we set our HO to be 170, there's no difference. Then the alternative hypothesis can be tested in one of the 2 ways, either greater than 170, not equal to 170. Not equal to 170 is called a 2-sided alternative, because if we say not equal to 170, that means it can be either less than 170 or greater than 170. So that's a 2-sided alternative. So that will take us to the second step. So again, the first step in hypothesis testing is to state our HO and HA, the null and also the alternative hypothesis. We can state it from our problem. So the problem we have, we state our problem. From the problem, we can get our HO. And when we get HO, opposite of HO will be our HA. Always the alternative hypothesis HA is always against the null hypothesis HO. Now we have to do our test statistics now. Here we are using the Z score to test our statistics. So we say this chapter introduced the Z statistics for one-way sample problems about means. So the first thing we have to do is to find the Z stat, which will be we collected a sample mean. So the sample that we collect, the mean sample minus the population mean over the standard deviation of the sample. And the standard deviation of the sample is called the standard error. And we know that to find the standard error, It will be the standard deviation of the population divided by square root of the sample size. So we continue with the example that we have. We remember the mean was 170. So now we take a sample. The size of the sample is 64. And we say the standard deviation of the sample we took, or of the population, is 40. So if the standard deviation is 40, then we can find the standard error, which will be 40 divided by square root of 64. So we have 40 divided by square root of 54, and that gives us 5. So the standard error will be 5. The next step, we can find the z-stat now. So that is the sample mean minus the population mean over the standard error. And in our first sample we collected, the sample mean was 173. So we have 173 divided by 173 minus 170 divided by 5. So that will give us 0.6. Then we collect a second sample. In our second sample, the mean was 185. So the z-stat will be 185 minus 170 divided by 5. And that gives us 3.0. Since we are collecting the sample from the same population, the standard deviation will be the same. And also the population mean will be the same. So now we know the two z values. We can go to our table, but before that, we also assuming here we take as many samples as we want. We take a third sample to be 164, the same thing. We can find the z-stat. We took all the samples, so our distribution becomes a normal distribution. This is the sampling distribution of the mean. So next, we are going to find the p-value. In order to get the p-value, we have to use the standard normal table because we are using the z-score test. So the standard normal table is the z table values. So we go to our table, the standard normal table, and our z value was given to us previously. Now, the only thing we should know here, which is our main interpretation understanding, is that when the p-value is very small, we have a stronger evidence against the HO. We are going to reject the HO. When the p-value is big, we are going to accept HO. So sometimes we have the significance level. The significance level is, let's say, represent alpha, and it's given to be 0.1. It means if my p-value is less than or equal to 0.1, I'm going to, again, reject HO. But if it's greater than 0.1, which is the significance level, then I have to accept the HO. So let's go ahead and then get a drawing here. So we know our population mean was 170. We are doing our first sample. Our first sample, the mean was 173. And remember, the HO, we say greater, the weight is greater than 170. So we are looking to the right side. So when we go to our standard normal table, the value that we get, the z value that we get, will be from left to 173. So the answer we get, we are going to subtract it from 1, and that will give us 0.2743. And the second one, the mean was 185. So the same thing is greater, so it will be on the right side. So we are going to find the value from left to, and then z-score was 3.0. So the answer will give us some big value, 0.99 something. We subtract it from 1, we get 0.0013. So that will be our second P. Now we have to interpret it now. Since this p-value is very small, we said we're going to reject HO. The previous one, the p-value was a little bit more than 0.1. So we have to accept HO. And I think that's the next slide. So here they say that if we are doing a two-sided, what we just did is for and the HA is greater than 170. Now, if we say HA is not equal to 170, it means two-sided. So we follow the same step, but after we get the p-value, we multiply by 2, two-sided. So this gave us 0.0020. The second one, we have 0.2743. If it's two-sided, we multiply by 2, and that gives us 0.5486. So when it's greater than 170, whatever value we get for P, we keep it. But when we say it's not equal to 170, it means two-sided, the left and the right. It can be less than, it can be greater than. So we multiply by 2 when we get a p-value. So next, this will take us to what we call the significance level. Now we say earlier, as the p-value gets smaller, we have a strong evidence against the HO, which means we can easily reject the HO. As the p-value get bigger, we accept the HO. So this is all. Here we say, although it's unwise to draw firm cutoff, here are some conventions. Again, this is just a convention based on the textbook. So we said that, okay, if P is greater than 0.1, then we have non-significant evidence against HO, which means we have to accept HO. Now, if its P is between 0.05 and 0.10, then we marginally significant against HO, which means we can still reject HO, but not strong evidence. But as we can see, the P gets smaller now from 0.01 to 0.05, we have a significant evidence. Then when it's less than 0.01, which is very small now, then we have highly significant and strong evidence against HO. So about most questions, they are going to give us the significance level, which we represent as the alpha value. So our example, we get our P to be 0.27, and we know 0.27 is non-significant evidence against HO. We accept HO. The second P was 0.01, which is very small, so we significantly evidence against HO. So we 100% reject HO with P equal to 0.01. So the whole concept is, again, P is, as P gets greater, we accept HO. As P gets smaller, we reject HO. So we also have a decision based on the alpha value. Again, the alpha represents the significance level. So the alpha value. So here we say, let alpha represent the probability of erroneously rejecting HO. We set the alpha threshold of acceptable error. So we can set it to 0.10 or 0.05 or whatever level is acceptable. Then if we know the alpha level, the value, then here, for example, anytime our P is less than or equal to the alpha, we reject HO. And if P is greater than alpha, which means P is getting bigger, then we accept HO. So the example we have, we set alpha to 0.10. When we find our P, we get 0.27. So which means P is greater than alpha, so we accept HO. By the second example, we set our alpha to 0.05 and P was 0.01. So since P is less than alpha, we reject HO. So this will take us to one subtopic, which we call the one sample z-test condition. One sample, again, z-test condition. In most of our tests, these are some of the few items that, again, have effect on the condition for the testing. So for example, we should have a quantitative response. We should have a good data. We should do a very fair random sampling, simple random sampling. Also, the standard deviation should be known, not calculated. Population also should be approximately normal or sample large, which is the central limit theorem concept. So if I have HO, which is a null hypothesis, we say the mu equal to mu O. These are the three possible tests we can do. So we can say either the HA is not equal to mu O, or the HA mu is less than mu O, or HA mu is greater than mu O. So greater than will be on the right sided, less than will be on the left sided, and not equal is both sides, so it's two-sided. Then we do our test statistics, which we say the Z-stat will be the sample mean minus population, or the mu for the null or alternate null hypothesis, divided by the standard error, which is again the standard deviation of the sample, which is again the population standard deviation divided by square root of the sample size. So when we get our Z, we look for the p-value. When we get the p-value, then we compare it to the significance level or the alpha. So let's try this example. Here we have an adult score, intelligence score, and we say the score are normally distributed, or they are normal, with a mean of 100 and standard deviation of 15. Now we take a sample of 9, and the 9 sample, this is their score measurement, 116, 128, 125, all the way to 118. And now we want to do some testing here. Our goal here is that we want to test if maybe this, let's say this score was taken last year, and now we want to know this year if the score either is greater, less, or not equal to 100. So since the values are given, we can find our own sample mean. So sample mean will be adding all the 9 values, then divide by 9. Now, if I know my sample mean, I know my population mean, I know the population standard deviation, then I can find the standard error. Standard error will be 15 divided by square root of the sample size, which is 9. And that's in the next slide. So again, the first step, we set our hypothesis. The mean was 100. We are doing one-sided, so we have the alternative hypothesis that the mean is greater than 100. So as we said earlier, we find the standard error, which will be 15 over square root of 9. The population standard deviation divided by square root of the sample size. And that gives us 5. We calculated sample mean already, which is 112.8 minus the population, or the null hypothesis mean, 100, divided by the standard error, which is 5. So we get 2.56. Then 2.56, we are going to use our standard normal table to find our p-value. So we say Z should be greater than or equal to 2.56. It means whatever probability value I get for 2.56, I'll subtract it from 1 because it's greater than to the right side. And that gave us 0.0052. Now we are going to compare with our significance level was 0.01. So since 0.01 is greater than 0.0052, we said that we are going to reject HO. Reject HO. So these are the steps for hypothesis testing using again the Z score. First, we state our problem. Second, we state our HO and HA mean values, or their values. Most of the time, the HO is given. So that's why we say it's no difference. Then HA value always will go against HO. So after that, we find the Z stat, which will be the sample mean minus the population over the standard error. Standard error again is the standard deviation of the population divided by square root of the sample size. Then when we get a Z, we go to the standard normal table to get the p-value. Now, if it's greater, then we go into the right side, we subtract the p-value we get in the table from 1. If it's lesser, then we keep the p-value we get from the table. We do not subtract because it's on the left side. Now, if we are doing two-way, when we get our p-value, we multiply by 2. Then we compare the value to the significance level. If the p is less than or equal to the significance level, then we reject HO. If the p is greater than the alpha significance level, then we again accept HO. So this is another question, the same question, but this time we are doing different. The previous test we did was one-sided, greater than 100. Now we are going to do not equal to 100. So the steps are the same. We state the HO and HO already, we find the Z already, and we find the P. But this time when we get the P, we multiply by 2 because we are doing two-sided. Not equal is always two-sided. So we get the p-value to be 0.0104. Then we are going to compare it with the significance level. If the significance level is 0.05, then we are going to again reject it, HO. Or if it's 0.1, we're still going to reject. So since p-value is less than the alpha value, we are going to reject HO. So this is how the two-way looks like. So we have two parts, left and right tail. So that's why when we get the p-value 0.0052, we multiply by 2 to include the left tail also. So this will take us to the next subtopic, which is the power and sample size. So in our hypothesis testing, we also have two types of decision errors. Type 1 error is when we reject a true HO. The HO was good, true, but we reject it instead of accepting it. Type 2 error means when we accepted a false HO. So the HO that we're supposed to reject, we accepted it. And we can see this in the truth table here. So for example, we have decisions either to retain HO or to reject HO, and whether HO is true and HO is false. So we can see this is a type 1 error. Why? We reject the true HO. And this is type 2 error. Why? We retain the false HO. So we represent a symbol as probability of type 1 error, and also the symbol beta as probability of type 2 error. So probability of type 1 error is the probability of, again, rejecting a true HO. Type 2 error means probability of accepting false HO. So this will take us to power. And what is a power? We say traditionally, hypothesis testing paradigm consider only type 1 errors. Again, type 1 error is when, again, we reject true HO. However, we should also consider type 2 errors. That's when we accept false HO. So beta here means the probability of a type 2 error. N is 1 minus B, and we call it the power. So power refers to as probability of avoiding type 2 errors. Again, the power is the probability of avoiding the type 2 errors. And we have a formula for it. So 1 minus beta is theta negative Z 1 minus alpha over 2 plus mu O minus mu A. Now, mu O is the mean for the null hypothesis, and mu A is the mean of the alternative hypothesis. Then N here is our sample size, and then we have Z 1 minus alpha over 2. So alpha is our significant level, and whatever value we get here, we look for the Z value in our standard normal table. So we are going to do, again, the same problem we had previously, the weight. So we know the sample size is 16. The weight, we say the mu is 170 and the alpha is 0.05 and it's two-sided. We are doing the one we say HA, the mu is not equal to 170. So what was the power of the test condition to identify a significant difference if the population mean was actually 190? So here, actually 190 means our alternative hypothesis mean. So we can see the formula again. Now, the alpha is 0.05. When alpha is 0.05, your z value will be 1.96. Again, we put 0.05 here, we find the result of this. So we get 2, and 1 can go into 2, so 2 minus, there's 0.5 here. So again, when you do the calculation, the answer you get here, 1 minus 0.05 over 2, the answer you get, you look for the z value of it, and that will give us 1.96, but there's negative here, so the negative will come. Then the difference of 170 and 190, the alternative mean and null hypothesis mean, then multiplied by square root of the sample size divided by the standard deviation, 40. So when we do our calculation finish, the answer here will be 0.04. Then when we get 0.04, we go to the standard normal table to go and find our value P, which will be, in this case, we get it to be 0.5160. So here we say the probability of avoiding type 2 error will be 0.5160 or 51.6%. So the reasoning behind the power, here they say we should consider 2 competing sample distribution models. One model will assume HO is true, which is the next page, the top curve, and then another model will assume HA is true. So this is why we say the power is the probability of avoiding type 2 error. Again, type 2 error means when we accepted the false HO. So when alpha is 0.05 two-sided, we will reject HO. When a sample may exceed 189.6, that's right tail top curve. The probability of getting a value greater than 189.6 on the top curve is 0.5160. And we'll see the curve here. So we can see here we said we'll reject HO when the sample mean exceed 189.6. So somewhere here, 189, we will reject HO. So this is our sample distribution of the X bar or the sample mean, assuming HO is true. And this is a sample distribution of S bar, and we are assuming HA is true. So we can see that here we have 190. We are assuming 190. 190 is the mean of the HA. So the power will be 0.160 in this greater section. And then last part of this lecture is how to get a sample size requirement. Sometimes we may have a test. Always our test will be based on sample size. We said earlier, sample size can have effect on our testing. So sometimes we may have a condition, if the sample size is too small, we can't do a t-test or f-test. So we may have, we should have some amount of a sample size. So here, if we know the power, the z value for the power of our avoiding type 2 error, 1 minus beta, and also we know the z value for the alpha significance, or 1 minus alpha over 2, that is the significance level. If we know these two values and we know the standard deviation, and we know the mean for the null and also the alternative hypothesis, we can find the n, which is the size of the sample. So again, here 1 minus b refers to the desired power of the test. And the desired power of the test is the probability of avoiding, again, type 2 error. Then we have the alpha, which is the significance level, the desired significance level. We also have the sigma, which is the population standard deviation. And we say the delta is the difference of the mean for null hypothesis and then a mean for alternative hypothesis. So we are using the same example again, but now we are saying that how large a sample is needed. We want to know the large sample that is needed for one sample z-test with 90% power. And also the alpha significance level is 0.05 two-tail when the standard deviation is 40. So based off our null hypothesis, we are assuming the mu is 170 pounds and the alternative we assume is 190. So we look for the difference. Mu O minus mu A will give me 170 minus 190, which is negative 20. So we have negative 20 squared from the formula. Then Z1 minus beta, that will give us 1.28. Again, we have 0.9 power. But when we get the answer here, we have to look for the Z value of it. And also alpha is 0.05. So when the answer we get here, we look for the Z value of it. And that is 1.96. So when we do our calculation, we should get 41.99. This tells us that we need at least a sample size of 42 in order to do this test. So again, this is the diagram, 182.3 and 0.025 to the right, 0.05025 to the left. This is a again 2 tails 0.5. So that will be the conclusion. That will be the conclusion of, again, our lectures on hypothesis testing. Again, as we said, this is the basic hypothesis testing using, again, the z-score value. So in these lectures, we went through the 4 steps of testing and also the difference between type 1 error and type 2 error. So the 4 steps, again, is first, we have to state our problem. From the problem, we can state our HO, the null hypothesis. We can also state the HA, the alternative hypothesis. Then from there, we again find our test statistics. From the test statistics, again, we can find our p-value using the standard normal table. Then after we get our p-value, we have to make our statement whether we reject or accept HO. If the p-value is less than the alpha or equal to alpha, we reject HO. If it's greater than the alpha, which is the significance level, then we accept HO. And also, again, we learn what is type 1 error. Type 1 error means, again, rejecting the true. And also we have the type 2 error, accepting the false. That's type 1 error means rejecting the true HO. Type 2 error means accepting the false HO. And also we learned about power. Power is the probability of, again, avoiding the type 2 error. And also we saw the formula of how to calculate the sample size that is, again, required for our studies. If we know the mean for both HO and HA, and we know the power, and we know the significance level, then we can find the sample size required. So again, wish everybody the best. And in our next lecture, we are going to continue with our hypothesis testing. Thank you.